Okay, so then let me start now. Finally.
Yeah, sounds good.
Okay, so all right. Good morning, everybody. So this is a tutorial on dispersion of mobile robots on graphs. Basically, myself, Anisur Rahman Mullah, and William Kumar Moses Jr. We are going to present it, and thanks to Shreyas Pai, who is actually helping us in this. Like we could not make it to PODC in person, but Shreyas is actually coordinating it. Thanks to Shreyas. So this is the roadmap of this talk, basically of this tutorials. For the first half, like for the first 1 hour, I am going to talk about this foundation of this problem and some initial classical results. And then in the second half, Billy is going to take over, and then he's going to talk on some extension of it, some advanced research what is done on this, on various types of settings and what's the current state of the art. So let me start with the problem definition. So what is a dispersion problem? So dispersion means like you have to disperse the mobile robots on a graph and like this. So initially the robots could be, let's say you are given a distributed network and it's an anonymous network. Let's say nothing is known to the network, but only the, let's say, edges are somehow they are connected. So the robot has to move through the edges, like from one port to another port and go to another node. But initial configuration is like robots can be at anywhere, right? So it can be like grouped at single node, or it may be grouped at multiple nodes. It could be anywhere. So that's the initial configuration we say. So they are arbitrarily distributed on an n nodes. And so what we want, the dispersed configuration or the final configuration, that is finally all the robots should be, each node has exactly one robot. Exactly one robots when basically there are n robots are starting, because it's n nodes graph. And we have a more general definition. If there are k robots, we'll come to that. But think of like n robots are starting arbitrarily. And our goal is to reach to this final configuration where each node holds exactly one robot. Okay, so that's it. Now what we do, basically, we study how fast can we achieve this dispersion with limited number of memory at each robot. So let's say if robots have very limited memory, then how fast can we do that? So there is a trade-off, right? So there is a trade-off between running time and memory per robot. So that's the problem. Okay, and what model we, of course, the model is very important in this cost context. And first we discuss graph model and robot model and time model. So what is the graph? So a graph is just like connected, undirected, and unweighted. Although very recently there is a study on this directed graph. But let's focus for this tutorial mainly. For this, at least for this first part, for this undirected and unweighted and connected graph. And it's an anonymous graph. That means nodes do not have any IDs. They are indistinguishable, right? Like robot cannot distinguish between two nodes. Okay, and there is no memories also on the robot, so that you cannot store anything on the node of the graph. But the ports are numbered. Let's say at some node U, it has the degrees small delta, and the ports are labeled, let's say from 1 to delta, but there is no correlation. Okay, so ports at each node, they are numbered. And this is a standard notation we use. Basically, the G is the graph, and N is the number of nodes in the edge in the graph, and M is the edges. D is the diameter of the graph, and the maximum degree, delta, big delta. So these we use for, these parameters we use for like showing your time complexity, message complexity, and other things. Okay. So these are the standard parameters we just assume. And it looks like this. So this is a graph. There is no port numbers. There is no node IDs, but ports are numbered. There is no node memory. Okay. This is just an anonymous graph. And the robots are arbitrarily distributed here. And our goal is to disperse the robots so that each node holds exactly one robot. What is robot? What is the power of robot, model of robot? So robot here, basically, we are considering like the robot is not oblivious. Basically, they have memories. So each robot has some memory. Typically log n bits. If there are n robots, if we want each robot has unique IDs. So at least, we need O of log n bits for that, right? So typically it is log n bits. Let's assume that. And what is the communication? The robots can only communicate when they are at the same node. So that means And this is we call local communication. There is also a variant of it. It's called global communication, where a robot can communicate with any other robots in the graph. Doesn't matter wherever it is. But I mean, initially the studies, I mean, it studied actually this just for this person is we studied. It's just considering local communication when the robots are at same node, so they can communicate. Physically, they can exchange message. They can. That's the communication. And port information is when a robot moves from a node U to V, the graph, so it knows both the outgoing port at U and the entering port at V. That port number did not be same, but I mean that robots can see that, like what is the port number it is taking and what is the port number it is entering some node V. Okay, so that's the power of this robot. The time model, of course, like the synchronous model means like time is divided into discrete time slots, or that's we call rounds. And time complexity is the number of rounds until dispersion. Like if we start from the beginning, like initial configuration, how much time it will take to complete the dispersion. And there is a memory complexity, that is here we have number of bits per robot, because we assume that there is no memory at node in the graph. So robots have memory. So how much memory they use. And another thing is, this is we are considering CCM model, like a robot perform these 3 tasks in each round: communicate, compute, and move. That is CCM. Okay, what is communicate? The robots, when they are at the same node, they can communicate with other robots. So this communication you can think of like they can do via, like they can scan others' memory, right? So let's say some memory they put it, I mean others can see it, other can read it, or they can exchange via some other way. I mean that's like, it's like observes memory of itself and others. That is a message exchange. And they can compute. What is compute? They perform some local computation. And after computing something, they decide which port to use to go, whether to move or not, whether to store something. So that's a part of local computation. And the move part is like, if they decide to move, then they move to that, I mean through that particular port. I mean during the local computation, they decide which port to use, I mean to move, and they use that port and move the next node. So that's it. Okay, so in each round, basically a robot can perform these three tasks: communicate, compute, and move. So let me recall you, I mean the dispersion problem. This is general definition. Let's say there are k robots arbitrarily distributed or arbitrarily placed on an n node anonymous graph. Our goal is to reach to a configuration where a node has at most ceiling of k by n robots. And our goal is to do this, to reach this final configuration in as few rounds and memory per robot as possible. So you can see that trade-off between robots and the memory robots and the time, right? So if the robot can store many things, so that means it can store the like full graph, like until where it moves. So then the expectation is it can complete this dispersion like very fast. So that's the trade-off. So our goal is to basically use less memory and complete this dispersion very fast. And just consider, I mean, we considered the simplified version when we just, for this talk at least, I mean, because for general K, it is, you can easily extend it. But let's assume K is n, like there are n node robots, n node graphs, and there are n robots. Okay, that means each node must have exactly one robot in the end. That's the dispersed configuration, final configuration. Okay. And also there is we study, I mean, we differentiate between arbitrary configuration, like the initial configuration we differentiated in this two way. One is we call rooted configuration, like if all the robots starts in the beginning, initially from the same node, like they are placed in the same node in the beginning, then that we call rooted configuration, okay, or gathered configuration, because they are starting from the same place. And the other is arbitrary configuration, basically if it is not, like if the robot starts from multiple nodes. Okay. So it's rooted configuration and arbitrary configuration, these two definitions. And you can see that, I mean, you can imagine in this problem is actually, although this, I mean, very recently studied, I mean, I will tell you when it started, but this problem is very good. I mean, it's related to all other like graph exploration, the graph problems like graph exploration, where every node must be visited by a robot, right? The gathering problems, gathering in a graph, like all the robot must meet at the same node, or scattering, covering, deployment, these types of problems. You can see that relation. Also, you can think of like, this is a load balancing. You see like let's say the robots are kind of load, or it's actually carrying some loads. So your goal is to place them in different places. So actually what we are doing in the end, if there are n robots, so our goal is to place like one robot per node, right? So that's basically you are balancing the load uniformly, right? And I mean, whatever application you can think of, like for the exploration, gathering, scattering. So you can think of this. This application of these dispersion problems are all same, because they are all related. I mean, if you solve one, maybe you can solve others, but it's not always true. I mean, that we will discuss later. But another thing is the relocation of self-driving cars, like as an application. You can think of like, now we have like coming like this era of like self-driving cars, right? And you can think of like they are like driving by robots or somehow, and they wants to find some free or empty recharge station. So let's say that they are the nodes, somehow they are related. And load balancing and robot deployment, if you want to deploy some robots in some building, or to do some basically do some tasks, so this can be used. And this is studied in different settings. As you know, like there are different types of settings in distributed computing, and synchronous, asynchronous time model, the local communication, global communication. Let me recall you, the local communication means when the robots are at same node, they can communicate. And global means it doesn't matter wherever they are, they can communicate. Okay, so any robot can communicate with any other robots in any other node. That's a global communication. And let me give you, I mean, that some works that already that have done. I mean, so let's say the first, it is started in a few years back in 2018. First, basically, it started by William Kumar Moses Jr. and John Augustine. They actually introduced this problem. And then later, immediately, I mean, you can see there are huge work has been done on this problem, and still, I mean, people are working on this. So, I mean, there are different types of work. Let's say some advanced work, I can tell you, like the faulty robot. So the robot can be faulty, right? Either crash fault or maybe the Byzantine fault. So then whether we can achieve this dispersion, what is the time complexity? This also studied. And then in dynamic networks also. So besides, if the network is dynamic, if something is changing, and then still whether we can achieve this dispersion, that is also studied. And there are randomized algorithms also. So most of the works you can see they are deterministic, but few works, randomized algorithms are also there. So we'll discuss them later. And let me go a little more detail. What are the works? So let's say I consider the synchronous and local communication model. So it's synchronous and local, means robots can communicate if they are at the same node. If k is the number of robots, let's say k number of robots, n is the number of nodes, m is number of edges, and d is diameter, and delta is the maximum degree. In the first work, I said like it's introduced by Augustine and Moses Jr. that came in ICTCN 2018. So that's result actually they published. That's the introduction of this problem, and then they got some results, like if the memory is log n, the main arbitrary graph result, you can solve this problem in mn time. And if the memory, you can do a little more memory, like n log L memory, so then you can solve this problem in O of m time. Okay, and they studied this problem for for tree, cycle, and other types of graphs. Okay? And later, immediately this problem, I mean, some came up that Semikolani and Ali, they just also extended this problem a little bit. And then that another problem, I mean, then in our general graphs, like that's actual improvement is done by the Semkolani, Molla, and Sharman's algorithms at 2019. If you give like log of k plus delta memory, then this can be solved in minimum of m k delta times log k this time. But for this problem, I mean, like the third one, so for this one, it requires that robots should know these parameters m, k, and delta. Later in 2020 SS, the Sintaku et al, they published, I mean, they actually extended this without knowing this parameter also. This is solvable with the same message, so the same memory and time. And I mean, this last year, I mean, Semkolani and Sorma, they actually even they improved by this log n factor. You see, like with same memory k plus delta, it can be the dispersion can be solved in minimum of m k delta time. although it doesn't work for, I mean, it is for, I mean, this optimal, this is like kind of, I mean, for some cases, it gives you optimal results because you need at least k time. So k is the minimum number of time that you can see easily, right? So let's say for constant degree graph, it gives you optimal time. Okay, so this is the so far the best result in arbitrary graph, and it's undirected graph and connected undirected graph. This is the best result so far, the last one. And then if you consider the different types of graphs, let's say the path ring, I said, like in the first paper itself, the Augustine and Moses Jr., they actually solved, I mean, they gave some efficient result with log n memory, this path ring tree. So you can solve in O of n time. And for the rooted tree means in a tree where all the robots are starting from the same node. Okay. So that with log n memory, it can be solved in d squared time. D is the diameter of the network. And in grid network or mesh network, that is with log k memory, it can be solved in k minimum of k square root of n time. Okay. Square root of n is the basically the diameter of the grid. So this is the result for the other types of graphs in local communication model. But what we get in global communication model? So you see, the local communication means like robot can only communicate if they are at the same node. But in global communication, they can communicate when they are at different nodes. I mean, doesn't matter in any nodes they can. I mean, with a robot can communicate with any other robots. So you have some extra power, right? That you can see. But the point is, I mean, you cannot actually. So that paper by like Shemkalani, Molla, and Sarma, they showed that. I mean, we can. I mean, although you have this extra power, but it's not actually useful to achieve more faster algorithm. So we can only get this. You see this MK delta is the same time they recently got it. So what is the reason? The reason is, I mean, although we do not have any formal way of lower bound proving that you cannot achieve, but the intuition is here. Basically, although you can, in a global communication, a robot can communicate with other robots far apart, but it doesn't know where it is. It's in neighborhood, or it's a far apart, or even if they are in the neighborhood, it doesn't know in which neighborhood, right? So that's difficult to know. Because it's a broadcast, you are sending something like some broadcast message and everybody can listen it. So it's very difficult where they are. Their location is not trackable. I mean, you cannot look at them. So that's the weakness of this model. Although like you can communicate globally, but that might help you to break some symmetry global. So let's do all together this now. Let's do this. So that way you can break the symmetry. Also, I mean, another thing is in a grid. I mean, if you have a global communication, you can do actually this optimal with log k memory. You can do optimal square root of k time for any number, any k robots. So if k is the number of robots, so let's say k is less than n even. So still you can do in square root of k time with global communication. So that's basically so far the results in global communication, only two. And then in asynchronous setting, I mean, asynchronous and local communication, there is some extension. I mean, you can think of like, so you just extend this synchronous time setting to asynchronous, and they you get basically the time is with log k plus delta memory, the time complexity is mk time. Okay, m is the number of edges in the graph and k is the number of robots. And later in the same way, I mean, they actually improve this a little bit. So it's, you can do actually minimum of mk delta time in asynchronous settings. So these are the results. I mean, at least the results in this like connected undirected graph with local communication, global communication, synchronous, asynchronous model. But there are other advanced results that my colleague Billy is going to talk in the next part. So let me tell you some classic, I mean, some basic, I mean, some initial results or some initial algorithms on arbitrary graphs. Okay. So any questions so far regarding this model, problem definition, anything?
Yeah, no questions so far.
Okay, good. So let me then give you some idea of these algorithms, the basic algorithms. Okay, so what we have to do, like we have to basically place the robots, I mean, on some nodes, right? So essentially what we do, you have to traverse the graph. So, and There are two commonly used graph traversal method. That is, one is BFS traversal, breadth first search traversal, and another one is DFS traversal, right? Depth first search traversal. This is the most two standard, I mean, or commonly known deterministic traversal, I'd say, like on graph traversal strategy, right? So of course the basic algorithm, I mean, whoever start with this problem, they try to use these two. But this BFS traversal, the breadth first one, it is not efficient with limited number of mobile robots. If you have a few mobile robots, it's actually not efficient. Why? Just consider this scenario. Let's say all the robots are starting from the same node. See, so between the rooted configuration and this is rooted configuration, right? So all the robots are initially starting from the same node. And if it is arbitrary configuration, means like robots are starting from the different nodes. So they can be multiple groups. But you can imagine that this rooted configuration is intuitively is easier, right? So because they are all at the same node and they are starting, at least you can easily, I mean, you can have some easy algorithm to achieve. Maybe that may not be efficient or whatever, but still that's like easy configuration. Just consider this one in this graph. And if you want to apply BFS traversal to disperse the robots so that each node has exactly one robot. So how do you do? Like first, from this route, you can send it to UVW, right? Because its degree is 3, it can send three robots. Okay. And then at UVW, this UVW, they might form an arbitrary graph. Okay. And they do not know how many common connections are there, right? So they might have a many common edges between UVW. And also another thing is W does not know, let's say W does not know what is the number of robots required in its let's say the subgraph. It's not again such, not a subtree, it's a subgraph, right? Because for the subgraph you need so many robots. So that means W's demand is the number of nodes in that subgraph hanging from W. So this part is not possible. It's very, I mean, not, I should not say not possible, but it takes long time to get this, because even if you, let's say you send some, it's not like a message communication model, right? So you have to send a robot to get the information, and then you have to send back the robot to get that, to basically convey that information. So this way it is not efficient. That's what I'm saying. Rather you have BFS traversal, let's say depth first search traversal. It's a little slower. Slower means like, of course, if you can solve, I mean, if the BFS takes like from one side to other side, if it is possible, it's diameter, right? Or let's say diameter square, whatever. But DFS takes actually at least omega m time, right? So m is the number of edges in the graph, but it works for any number of robots. So because if you start from that and then you are performing DFS like one by one, you are settling, you just go and then you count, right? So it's slower, but it's actually works for any robots. And more, I mean, surprisingly, all the existing algorithms are based on this approach, because we know that like so far the DFS approach, BFS approach is not that efficient. So if you use DFS, still you are getting better, I mean, better efficient and faster results for this dispersion. And let me actually tell you the first two. So for the first paper, I mean, that is ICTCN 2018 by Augustine and Moses Jr. So you can see that the time is mn, okay? Or let's say the time is, the latter part is time is mk. So if there are k robots, let's say, or there are n robots, that means there are O of k or O of n groups there could be on a graph, and in this graph. And for each group, if you just basically perform this DFS one by one, it's a sequentially somehow, I mean, although you have to synchronize them, I mean, you have to coordinate something, but somehow if you can do one by one, then this much time it will take. Let's say there are k groups, and first group takes at most O of m time. So for k groups, mk time. That's very simple one, right? So you are performing, but the first algorithm, that is that Semikolani, Molla and Sharma, that AlgoSense on 2019 paper, what they did actually, they actually also started what they did, they actually started this parallel performing this DFS for parallelly. Parallelly means, let's say if multiple nodes, let's say there are two nodes which having as robots, okay? Like two groups of robots in two nodes. Then these two groups actually parallelly starting BFS, and when they merge, then they do something, and then basically this merging is actually a tricky part. And then by doing that, you can improve that minimum of m k delta times log f. So that's a huge improvement. That is the first like. And let's go with that algorithm. What is there? Okay. So this is the DFS based algorithm. So DFS traversal basically on an anonymous port level graph. That's basically our algorithm. And whenever during this traversal, whenever a robot finds some free node means where there is no robot, then some robot will come there and settle there. You are actually putting some robot there. That's basically trivial intuition. Now, if you consider the rooted case, let's say all the robots are started at the same node. Okay, if all the robots starts at the same node, then what you do? You just simply do DFS, and DFS that will take O of M rounds, that you know. Okay. And what you do, since I said like there is no memory on the nodes, so the already settled robots can be used. I mean, the memory of the already settled robots can be used to store some information. Let's say during DFS, you might have a package, like you might come to the same node, right? And then if it's a package, means some already robot is there. So that robot can help you, give you some information. So using that, actually, it's not difficult to do in O of M rounds. But if it is another case, if it is a dispersed case means, let's say initially all the K robots are on different nodes. Okay, but that means they are already dispersed. Then you don't need to do anything. So if basically all the settled robot means if there is a robot in one node, so that robots will not do anything. So it's basically settled. That means for this dispersed case, you don't need to do anything. Now for the other cases is like, let's say that's arbitrary configuration, means like robots are in multiple nodes with multiple groups. Okay, multiple groups of robots are at multiple nodes. Then what you do, that's the difficult part. Now each group basically runs DFS in parallel. Let's say there are K groups or R groups, so they are all performing DFS in parallel. If no DFS traversal trees meet, if let's say I started with a very less number of K robots, K is, let's say, quite less than N. Okay, so it could be the case that they do not even meet. Then what will happen? Then it's fine. Basically, if do not meet, then you don't need to basically think of how to merging them. But now, if two or more robot DFS trees they meet, then that's the task. Like, how do you basically how do you merge that tree? Okay, that's the question. So this is the key issue. Key issue means what we do when two or more robots, DFS tree of robots meet, right? If DFS traversal are performed sequentially, that is fine, because that will take O of M K rounds. If there are O of K groups and each group is taking, let's say, O of M rounds, so that will take basically O of M K rounds total, right? So all the previous algorithm, they did it, I just explained. But now to speed up, what we need to do, we need to merge the DFS fast. Basically, you should not basically do this one by one. You have to do some parallel merging here, merging of the DFS trees. Just think of this. Let me tell you this, how it is working. Let's say this is the graph, and anonymous graph. Nodes do not have any IDs, but ports are numbered. Let's say this port is numbered. It's numbered arbitrarily. Okay, so it is, let's say, already numbered. Let's say 1, 2, 3. The ports are numbered. And initially the robots are, let's say there are 14 robots total. So they are it's a 14 node graph. And let's say in this, there are 1, 3, 7. These are the robot IDs. And there are robot IDs 2, 8, 10 here in this group, in this node. And then in this node, there are 4, 6, 9, 11. So let's say there are 5 groups. And here only 14 robots, that is in a singleton robot. So 14 will be settled here immediately. Okay, so that's the thing. It is settled, but it will be active, and it will be basically active so that it should inform others that it is there. It will not terminate. And in this context, let's say the initial configuration. Now, how this DFS traversal algorithm this works? So actually, this is a 15 node graph here. Now, how it will work? So each group, as I said, like each group, they parallelly start the DFS. So this is the first round. So in one round, and let's say this is the DFS tree. Initially, it has, let's say, there is 7, 1, 3 here. The 7 settled here. That's why this node has 7. If you can see my cursor. So this node has 7, and then 1, 3 moved here. See, the basically idea of this DFS is always the maximum in the group will settle, and the remaining will move to the next node following the DFS traversal. And if the next node is empty, then the next minimum in this, the maximum in this group will settle. This way it continues. Okay. And of course, and you are also actually identifying each tree by, let's say, the ID of this, that's a minimum robot. Okay, let's say this is a DFS1, DFS2, DFS4, DFS5, DFS14. 14 is singleton DFS, so it's not moving. Okay. Now in the second round, what they do, they again perform DFS. Now you see this red color, like the DFS basically one, it meets with the DFS, this green color DFS, DFS2. Similarly, the DFS, this brown also meets the green DFS. Here, blue DFS also meets the red. So there are multiple meeting in round 2 itself, right? Then how do you do? How do you gather them? So that is basically what the idea is. What it's doing, it's doing basically the maximum. So ID of the DFS trees are there because I am actually considering the ID, in a group, let's say the minimum ID robots ID is the ID of the DFS tree. So now which has the maximum ID, that ID will continue and the minimum ID will wait. In fact, wait means it won't wait. What we are doing, we are actually gathering these robots to a node in the maximum ID. And so the maximum ID can continue. Okay. How it is doing? So this is the stage 1. So for this, it's actually runs into like we are in phases or passes. There are log K pass. And what we are doing, this is the two stage of algorithm. And these 2 stages are actually, we are passing it for log K passes. Okay. So first we are doing, so run DFS traversal from each group parallel. If 2 traversal meet, lower ID DFS traversal continues. And actually, this is opposite what I said. So lower ID continues. I mean, this is just a breaking the symmetry. I mean, you can take lower ID as higher ID or higher ID. You can interchange that. That's fine. So if 2 DFS traversal meet, so lower ID is actually continues and higher ID stops. They wait. And in stage 2, what they are doing, collect the unsettled robots in the waiting tree. Okay. If they are waiting, that let's say the lower ID tree is waiting, you are collecting to and gather them at some node. So you are actually taking all the lower ID trees robots to that node where it meets the other tree, and you are actually gathering them at the root of this higher ID tree. Sorry, the lower ID tree, because the lower ID tree is continuous. You are collecting all the robots of the higher ID tree because it meets and stops. It meets to a lower ID tree. Now you are gathering all the robots to the root of this lower ID tree. Okay, then they will start again. They actually extend that lower ID tree. Okay, that's the merging procedure. So this you are doing for all the DFS they are performing in parallel. Okay, now basically what you have to show that after each pass, the number of DFS trees decrease by at least half factor, right? So that's why log K pass is enough to merge basically all the DFS trees. So there could be, let's say, O of K groups, then log K pass is enough of log K pass. So that is that's why this log K factor is coming in the time. And you see that for each traversal of one DFS tree, at most O of M round will take, right? Because that is the O of M is the total traversal, the DFS traversal time. So at most so many O of M. That's why O of M time log K, that is the time. And so why now this K delta is coming? Because if K is smaller than it, K is, let's say, very, very small, let's say some log N or so, then basically this K delta is maybe less than this M. Okay. In that case, basically you don't need to visit all the nodes. After visiting, let's say, K nodes, you are done. But to visit K nodes, you might have to spend K delta time, right? During using DFS traversal. To visit K new nodes, I mean, you might have to spend K delta times, because you might be in a use that cycle or package delta times at most. So that's why it's minimum of M K delta times log K. Log K is the phases. So for this algorithm, we assume that they knows this parameter M K delta to synchronize it. But later in 2020, that Sintaku et al., I mean, they basically solved this without knowing this parameter. But the time and memory is same. And then last year, that another algorithm, I mean, that came, that is basically staking, it's actually improving by log K factor. In fact, you can do minimum of M K delta time. That is done by Semikalani and Sharma. So let me actually go and tell you what is how they remove this log N factor. What was the previous algorithm? The previous algorithm was basically you are running in 2 stages. These two stages running in, and each pass basically contains these 2 stages. One, first you are parallelly performing DFS, and in stage 2 you are basically collect the unsettled robots in the waiting tree, right? Those who are waiting in the waiting tree, you are collecting them and gather them at the root of that. Okay. Now instead of doing that, let's say, how we are breaking the symmetry here based on the IDs of the robots. So we are giving the ID of the robot as a tree ID. Now, later what they realized that actually if we do based on the size, if we break the size based on the size of the DFS tree, then it can analyze that you don't need even this log n factor. You don't need to actually pass this log n phase. Okay, log n times. Why? Because the idea is the sum of the, I mean, whatever be the trees, I mean, basically the DFS tree you are performing, that if the larger size DFS tree subsumes the smaller size DFS, it's a size, you are breaking the symmetry by size, then what will happen? The size, the sum of the size of all the trees, let's say there are k BFS trees, O of k, right? Whatever. But the size of the BFS trees, all the trees, it won't be more than O of m. Okay, that's the thing. So then based on, if you are merging the BFS tree, DFS tree based on the size, their size, then this actually you can do in O of m time. So you can actually, you don't need to run these log n phases, log n process. Okay. So that's the tree. So it's a very small tree, but it works. Like you should not do based on the IDs, but do the based on the size of the tree. Okay, and this is like the algorithm, I mean, for arbitrary graphs in connected undirected graph, and then as I said, like there are, let's say I can tell you briefly on the grid. So
Before you continue, actually, I had a question, Alisur.
Yeah.
Can go back one slide.
Yes.
Yeah, so here it seems like in the DFS algorithm, you're assuming that the number k is less than the number of vertices, right?
Which one? The letter one? This one? The 2021?
I mean, so does this, like, because you always leave like one robot at every node when you do the DFS, right?
Yeah. Yes.
So you're kind of assuming that you don't have very many robots, like each node
Yes, I
would
mean,
have
at least
two
I
robots.
assume that for this talk that k is at most n. Okay. K is
Okay.
at most n, but it is fine. Let's say if you have more robots, but in that case, I mean, you have to check. That's a good question. You have to check, like, if you need to know the number of robots.
Right.
Okay.
Okay.
And in that case, definition you can actually store in a one node at most, like k by n robots. If k is more than n, let's say k is n log n. Okay. If you are taking n log n robots, so at most, I mean, since it's a load balancing in a node, it should be log n robots, right? It cannot be more than that. But the same process you can do multiple times, and then you can basically load balance the remaining robots. But you might need to know the number of robots in that. I'm not sure actually. But so far, whatever you are right. So we are assuming that k is at most n. Yes. Okay. Yeah. Yeah. So then on a square grid. So grid is actually yeah, sure.
Yeah, I was wondering with this subsuming step, do the two DFS trees merge together, or do you just throw away the smaller one?
Shreyas, can you please repeat that?
So for the merging step, do you throw away the smaller DFS tree, or something else happens?
No, for the first, the previous algorithm, like this one, the stage 1, stage 2, where we are passing this for log n passes, they are actually what we are doing this the smaller, let's say whatever is settled. The remaining robots we are actually merging. Let's say T1 is one group and T2 is another group. So let's say T1 is smaller and T2 is, let's say, higher IDs. So then higher ID will, let's say, will stop, right? T2 will stop, and the remaining, let's say in T2 some robots are already settled. The remaining robots, it remains something, then it will be gathered to the group of this T1 group. Like the essentially what we are doing, it is actually extending. We are continuing extending that T1 group, and you have to push that robots to the where these robots are extending. But in the latter algorithm, the other one, what they are doing, so even if you collect them, if you, let's say in T2 or some robots are settled, but what they are doing, even if you can collect the settled robots also to the T1 group, all of them, still the time is fine, because within that order you can do that. You don't actually increase the order. So is it clear, or you still have?
Yeah. One second.
Yeah. Okay.
Doesn't matter if you throw this one or last one.
Right.
Yeah, actually, it's actually it doesn't matter. Even in the previous, we did that, but it doesn't matter even if you collect all of them. You know, I mean, asymptotically with the same time, and because the size is basically it will take the double size of the double times of the tree. So that's basically 2 factor will come, something like that. Maybe if you want to collect even the settled robots. Yeah.
Okay, that sounds good. Thank you.
Yeah. Okay. Yeah. So now for, let's say, square grid. So grid is like the mesh network is it's important network in this context, and it's I mean several papers you can see it studied over this grid network, and where we have algorithm like in local communication model that you can do if there are k robots and n node grids. Then what you can do, you can actually solve this dispersion in minimum of k square root of n rounds, and where you need O of log k bits per robot, the memory, okay, with so many robots. And this algorithm is not very tricky. It's actually a simple algorithm. Let's say first consider the case where all the robots are starting from the same, node. Let's say they are starting from the corner node. I mean, if they are not from the corner node, you can easily put them in a corner, right? Because you know, like the degree of the, I mean, if you can go arbitrarily to one side, any side, you can reach that with square root of n rounds. And then you can basically again go up or down, whatever way. So from the side of this grid. So that will definitely take. So just assume that this is as a subroutine we use, but there is a trick. I will tell you what is the trick. Just assume that all the robots are starting from the corner point. Let's say this is all the 25 robots is starting from this corner point. Then this is very trivial that you just send you, because if you know this n or the k, basically it's all the, it's n equals to k, basically it's assumed here. And then you just divide it by, let's say it's 5 group, because if there are basically square root of n way, you can do that. And then first you push them, I mean, in the side of the grid, and then the part is like once they are in the side, then you again you just send them, disperse them along the line in parallel in the second part. Okay, but the trick is here, how do you basically send this this line? Let's say 5 is here. Let's say once you send one, I mean, this one robot is settled here in this here, and then next, basically, if you can see my cursor, then the 4 robot moves here. Okay, so of course it knows that this is the, it has to move, because it knows that it comes via this, so it should not use this 2 port number. It takes the remaining port number to go here. Now the trick is how from this port number it will know that this is the port number, go to the parallel. It should not go this side, because that will create some issue, right? It should not go this way. So how do you know that this it should go? It's actually what we assume that, I mean, just to solve this one, so we assume that this is a planar grid, or it's on a plane. Now if it is on a plane, then you can just skip one port and take the next port and go, it is the line. I mean, but in this paper, this assumption is made. So this is a planar. If it is not planar, actually this is not solved. So that might be considered as an open problem. So otherwise it's a difficult, I can tell you. The tricky part is once it is here, it's coming from this port. So it knows that it is the entering port number. It has to take any of the 3 port, but which one is giving you this line? Because it should go this line. So unless it is, identify this port number or guess this port number, otherwise it's typical. You can go this side. That might actually increase your time. You have to settle something. But here we assume that this is a planar grid. So in a planar grid, you can easily, let's say the port you are entering, the next port you skip, the second port you just take, and that will give you the line. Okay. So this way you can go to the line by line. So, and you can finish this dispersion position. But this you can be used if the robot starts from arbitrary initial configuration. Let's say this is the robots, are so many robots. Let's say 25 robots are starting from like all these groups, like in this corner 3 robots, here 5 robots, here 8 robots. Okay, they are starting. And what is the trick? Then of course my goal is to first to gather them in some corner, and then from corner I use the previous algorithm. Okay. And how do you gather them in a corner? So it's also easy. It's not difficult. So what you do? So it's basically the robot 8, whatever line, it just sent to arbitrary line and swam in the same direction, unless it arrived at a node whose degree is 3. If the degree is 3, that basically it is already in the side of the grid, right? If the degree means you can know the degree by counting the port number, right? 8, this group, let's say the 8 group, it looks like it is in the middle, somewhere in the internal node of this, inside node of this this grid. So it takes just any arbitrary, let's say it takes this one, this path, and then it always follow that using that planar grid idea, that it's take the next port to go to the same direction. So it will move that way, so until it reached here and the side, and once it is in the side, is always take any of the side and always take the degree. Since it's a degree 3, it will always can go to this the next port, I mean will give you that. Okay, so this way you can go to the corner, but they might be in a multiple corner. Then how do you then gather them in one corner? That's also easy. Let's say based on the, let's say the IDs, or I mean, since we assume these IDs are basically it's not arbitrary. So based on the ID, you can break the symmetry. So some group with ID, let's say lower ID, they will wait, and some group with higher ID, they might basically move something. This way you can also in the same time gather them in a corner node. Okay. So this is the trick. So first in the part 1, if it is start from arbitrary, you just gather to all the robots in a corner node, and then apply from the algorithm from the corner node. And essentially it is taking the minimum of k square root of n rounds, okay, with log k bits per round, or log k bits memory per robot. Okay, so this is the state of the art in synchronous setting. You can think of like in a undirected connected graph. So it started in 2018, and then 2019. And then the big improvement is done by this paper 2019 in Algo Sensor and then so far the best result is this MK delta. And then now the next thing is actually we do not know whether we can do better than M. So, and another thing is, I mean, I can discuss a little, I mean, so whether M is the lower bound, deterministic lower bound, and deterministically whether M is the lower bound, the number of edges, because if you use DFS kind of things deterministically, I mean, with this, I mean, if you do not have many robots, I mean, if you have many robots, then might be it's faster. I mean, you can expect, let's say, if I give you n robots, n nodes graph and n robots, then so far you do not know, I mean, if there is a little of M algorithm. Okay, so that's a next thing. Other way you can think of like whether M is the lower bound. I mean, so far whatever our, I mean, we think we did not get to come up with, I mean, we did not come up with any algorithm which is actually little of M time. So don't know deterministically whether that is possible, or you can think of that. And state of art in asynchronous setting, it's just an extension from this synchronous to asynchronous. So this is the best one is like log k plus delta, with log k plus delta memory per robot. It can be solved in minimum of mk delta time. Okay, still, I mean, there is you can think of like what we can do later. Yeah, and so now let's discuss some open problems now. I mean, so I'm almost like for the tree and others, the other graphs, I mean, it's the algorithm is not difficult. You can use basically if it is tree, there is no cycle. I mean, it's actually easier. Okay, so you can use that. And even you can think of like applying DFS. So that's why there is a result. If you go there, I mean, it's taking d square time, because you have to come down, come up, go and down. You have to do that. That's the d square time result. So oops. Yeah, so this one. So this tree, you see like rooted tree, this is a d square time algorithm. It's basically applying DFS idea. And it's actually, this d square is actually a lower bound also. Right? So if there is many more robots, if there are many robots, then you can do even beat d square. But let's say with a limited number of robots, it's d square is the lower bound also. Yeah, for my part, so let me, so what are let's discuss something. So far, I mean, this distributed mobile agents or mobile robots, whatever, this is broadly studied in two categories, right? One is oblivious robots, where they assume that robots are memoryless, anonymous, indistinguishable. So basically that's the robot. Okay, so they do not have any memory. And it studies mostly over Euclidean plane and also graph also, but very less number of papers there. And mostly you can see with oblivious robots, I mean, they studied what is feasible, I mean, what is possible or not possible, like feasibility of a problem. If you are studying whether this is a feasible, not like analyzing the complexity, the time, memory, so that's not. But here, I mean, another part is like robots with memory, like if it is not oblivious robot, so that means robot has a memory. So with robot has memory, I mean, this is actually, that's what we are doing here. So this person is one such problem we are considering. That robots have memory and they are distinguishable. Let's say, since they have memory, they can easily have some ID, or even if they do not have IDs, you can assume that also, but still, but once you have memory, you can even randomly, because it's a processor, you can think of, they can randomly generate some number and give some. So that way you can think of like, they have distinct IDs and distinguishable. And they can also communicate. So they can share or exchange some messages, okay, something like that. So, and depending on like whether it is there in the same node or small different nodes, still they can do, I mean, they have some sensor that can be used to exchange some messages. And here we study what, like mainly the complexity, I mean, at least so far what we have done, like how much time or how much memory do you really need to solve some problem, okay, on graphs. So that's what we did. I mean, so then you can think of many other problems like in this model. I mean, I would actually, I mean, nowadays you see like that with robots, I mean, the memories are not that expensive. So even with small chip, you can have lots of memory, right? So then you can plug in that memory in a robot is not that difficult. So in a more realistic thing, I mean, even the oblivious robot concept is, I mean, should be, I mean, that, I mean, sorry, I mean, having memory in a robot, I mean, it's not difficult in practical purpose. And you can think of like other problems. It's not like dispersion, like think of like some other in this model, like where in a graph, you want to think of like how fast you can have like exploration or let's say scattering in this model, particularly model we are considering. Okay. So other problems can be started. And another thing is, as I already explained, I mean, this is a lower bound. So, so our conjecture is omega of m is the lower bound, because we do not know so far, I mean, any better algorithm which gives you deterministic algorithm, which gives you a little of m time. So this is the thing. I mean, we believe that maybe O of omega m lower bound is possible to show, but it is not yet done yet. And yeah, so let me stop here. I mean, so I'm done with this. So maybe and let me thank Gokarna Sharma. I actually adapted some slide content from him. And thank you. I mean, if you have any question, we have some time. So, but like maybe 4 or 5 minutes, and then the part 2 will start where you will see some advanced level studies like in dynamic networks, in fault tolerant setting, I mean, in faulty model, and some other parts that that will start in half an hour at 10:30. But now, if you have any question, maybe I have like a few minutes to answer your question.
So, what question?
Okay, I probably have a few questions. So my first question is about sort of how you presented it, especially at the beginning. You know, you're always talking about the amount of memory used by each robot. And at the beginning, you sort of said, well, there's a trade-off between memory and time. But sort of based on, at least my impression of the state of the art, is that there doesn't seem to be much intuitive reason why there should be a trade-off. Like, do you have any evidence that having more memory, you could get faster algorithms? Or if you have less, if you have less memory, like constant memory, would the algorithms take significantly more time? Like,
okay, constant time is of course not possible, because you see the n is the lower bound. N means number of nodes. Let's say in a path, you have all the robots and in same side, it has to move to the other side, basically diameter, you know, like one side to other side. So, and but if you have more memory, so this is the, I mean, you can see that this result, even the first result itself, or the second one, like even 2018, the first paper that introduced this problem. If you give, so with log n memory per robot, you can, it takes, let's say, mn time. Okay, or now the best result is m time, minimum of mk delta, okay, with log k memory. But if I give you n log n memory, that you can do with m time, right? And so this was, because this is the first one. I mean, we also do not, I mean, this is not yet explored. I mean, if you have more memory, what can you do? So the intuition here is, let's say, when a robot is traversing, it can remember some part of the graph, when you have memory. Okay, although because the ports are numbered, still you can basically use the like a map construction, you know? So basically the map of the graph that you can do, that might be help you to solve it faster, but it not fast as like in constant and log n time, because you cannot do more better than, I mean, you need at least n time. So that is the trade-off, is that's the reason trade-off is coming. And other thing is, let's say if you that's what, like memory, you asked memory, right? Trade-off between memory and the time.
Yeah, it's,
Oh, okay. Okay.
I guess, yeah, I guess based on what I'm looking at on the slide, there doesn't seem to be much evidence yet that there's a.
Yes, but now the thing is with so this m time, but now actually with this memory also, like you don't need memory, you can already also getting this m k delta time. I mean, with less memory also you are getting. But initially that like very trivial way is looking at, if you have more memory, you can do it a little faster. But this is, I mean, this is the, I mean, the intuition of the trade-off. But now the question you are asking, that sounds good. I mean, now if we have more memory, let's say n log n or n square memory, whether we can beat this m time, whether can we get little of m rounds algorithm with more memory, that might be a good question to explore.
There's also, I just want to add one thing that what Anisa mentioned. There's also another way to think about that trade-off. For most of what Anisa talked about, we assumed k less than or equal to n. And so with that, the time we conjecture the lower bound would be omega of m. If you take a large number of robots, maybe you could go even lower, because we do know that there's an iCal paper that talks about exploration of a graph, any graph, assuming you have a large number of robots. Something like if the diameter of the graph is d, if you have d into n power 1 plus epsilon robots, you can actually explore any graph in O of d time. The thing is, that's a large number of robots. Okay, you might ask me, first of all, that's exploration, this is dispersion. But I believe, if I'm not mistaken, that algorithm can easily be modified to also solve dispersion in a similar amount of time. So then you can ask yourself the question, all right, if we're hitting this O of m boundary with k less than or equal to n, let's boost the number of robots. Let's see what other trade-offs we can really see. That is something that's not explored.
Right. And on the other side, have you thought at all about constant memory, like, or sub-level memory?
So,
Yeah.
oh, sorry, Anisa, I'm sorry.
No, you can go ahead. I mean, my intuition is with constant memory, deterministic. I mean, you have to somehow break the symmetry. I mean, some way. Okay, so then I mean, one thing is, I mean, we have results with, I think with, I mean, randomized algorithm might be okay, but deterministically also, I'm not sure. I mean, with constant memory, whether you can do it. Okay, let's say one thing is, I can tell you, let's say if there is no memory, anonymous robots, then it's not possible, right? So if robots do not have, so that's the thing. So, but with constant memory, that's also a question. I'm not very confident to say, but I mean, Billy might add something. What I want to say that deterministically, what it might be, it may not be possible. I mean, I think there is a lower bound of omega log k, right, Billy?
Log k, if you want to just differentiate robots, if you allow randomness in there, it's log delta. And to answer the question there, there's at least okay. In the model we consider, where the port numbers are actually numbered from, say, 1 to small delta, where small delta is the degree of the node, you would need at least log delta bits of memory in order to actually differentiate the ports. So that is the minimum amount of memory you would need. However, just to add on to that, if you have something, if you assume a slightly different graph model, perhaps you can go lower. But for the current setting where even the ports have numbers that need to be read, log delta is a minimum.
Right. Yeah, I think it'd be interesting if you had, yeah, obviously you need log delta just to be able to read the ports, but probably the interesting measure of memory is how much you need to remember after you make your move. Like how much do you need to remember from previous rounds? I guess that's the important memory, other than the trivial memory.
That's a fair point. In almost all the algorithms, I believe we just bundle everything together, but that could be something worth investigating. Separating the amount of memory that has to be retained over time. Separating the working memory from
Right.
the permanent memory. That is a, what is that word called? That's a characterization of memory that I don't believe we've explored that. I do not believe we've explored that particular characterization of
Yeah,
memory.
actually do not differentiate that, but I also saw, I mean, some papers on they differentiate between that memories, but yeah, we haven't done this actually, but we have actually for dispersion problem, it is not yet done. Yeah, any other question, please?
I actually have a question. So this
Yeah.
goes off the like studying other problems part of your presentation in the open problems slides. Have people studied let's say graph problems in this model? So let's say you can think of the robots as like a mark on the nodes, and I want to disperse the robots in such a way that every node that has a robot is marked, and this set of marked nodes, for example, forms a vertex cover.
That's a good question actually. So yeah, this marking thing, I would say, like there are Shreyas, I mean, there are papers, it's called like whiteboard, you know. So nodes are basically anonymous, but they consider like each node has a whiteboard. So whenever robots visiting there, they can write something or mark something. Maybe it depends on the memory you need. Again, there is a trade-off in memory. So how much memory you use in your whiteboard. Okay, let's say each node has one whiteboard and robots can come visit. If you use only 1 bit or 2 bit, so that's like depending on, like, then you can do some marking or whatever. So based on that, I mean, you can do this is a different model actually. That's what. So that's a that's a whiteboard model it's called. Okay. And but the question like vertex over and others, that's actually very good question. So in fact, we are also thinking on it. This should be a good question, like whether the robots you are performing or whatever, even like the other things I can tell you, like the robots can you place the robots in a node such that the nodes forming a vertex cover? Okay. The same thing as maybe they are equivalent. This is a nice question, yes. And then you study the time and other things, you know, that memory space and whatever. Yes, I mean, but we believe, I mean, we should, I mean, we encourage to study this, like not oblivion, like robots with memory and what the robots can be, what can be computed via robots basically in a graph. So that way, because that is basically, this is the starting of this. And that's why like many people actually started this. I mean, you see, like it started in 2018 and then like they introduced this, and suddenly like in a few years, I mean, so many papers actually. And of course, this year, I mean, Sirocco also, there is a paper on even they consider directed graphs, and some results are there. It's a nice paper also, yes.
Another question about the model. So assume the nodes themselves are anonymous. What can you, does it become trivial if the nodes have IDs, or what could that help you, or is it a whole different set of results if the nodes have IDs attached to them?
Billy, did you get that?
Yeah. So the question was, if the nodes, all these results are for when the nodes are anonymous. That is correct. And then the question was, if the nodes have IDs, does this become trivial? That is also true, because the moment nodes have IDs, where it becomes highly trivial to just run a DFS. Oh, well, actually, sorry. Maybe I should take this back. With enough memory, it's very trivial. My personal feeling, though, even with limited memory, it becomes significantly easier, possibly bordering on trivial, because there's so okay. Here's one way to think about things. Anis sir talked about two starting configurations. The general arbitrary configuration where robots could end up wherever, and the alternative gathered configuration. Now, there is a common theme throughout a lot of these papers that whenever all the robots start at the same node, it's much easier, much faster. It takes less resources to solve the problem than if the robots were located in random places. The thing is, when nodes have IDs, a trivial, I would say, pre-processing step might be to scour the entire graph to find the smallest ID node and then sit at it and wait for some, I don't know, O of M rounds, such that all the robots can gather at that the smallest ID. Now, as you've seen here, we've conjectured that omega of M would be a lower bound for any running time. So this pre-processing step theoretically wouldn't add anything when it comes to asymptotic time complexity, but it would allow every kind of, whatever the initial configuration to be, you could end up at a gathered configuration, and then you run whatever algorithm you'd like. So I would say it, in my personal opinion, it trivializes the problem to quite an extent.
How would this pre-processing step work? Like, how do you? It's not obvious to me that it's trivial. It's the lowest individual.
Because you just do a TFS.
How do you do TFS? Like, unless you're doing something similar to the algorithm already, you don't know how to visit a new group. It's one that you've already visited.
Shreyas, can you please?
Small, there's so many of the dependencies.
So the question is about how do you exactly do it, the DFS now in this model with IDs. So the nodes have IDs. You don't have enough memory to remember the path you already taken. So it's kind of hard to, not easy to see that you can explore the graph quite quickly.
That is actually a fair point. That is a fair point, I have to say.
Oh yeah, I mean, if you do not have memory, even we don't know, like having ID, whether that might help. But in some context, it might help. I mean, not for DFS. You are right. I mean, sorry, not for the BFS. Even BFS, it's not. But one thing, like you can remember. I mean, if you can, at least remembering few nodes might help. I mean, not maybe for other like let's say in the faulty model, maybe believe that's the thing, right? So if you remember some visited node, yeah. Yeah, so essentially what I want to say, like having, you are just, if you are asking with ID, so having ID is of course a plus point, right? I mean, so but here, I mean, so to remember that, at least with, let's say if you have login memory or something, so at least you can remember a constant number of IDs with that, right? I mean, that is the that is way, but that might help you in some context, depending on like what you are doing. Let's say you can immediately go, let's say I mean, let me tell you like why I said this faulty model. Let's say if you are assuming that the robots have IDs, and just consider for now, I mean, the crash fault model. Okay, so robot might crash and it becomes basically completely inactive. Okay, so when a robot crashes, let's say it's still gone, so nobody can even see that robot. Now, let's say you perform this DFS or whatever, your exploding graph, and you already settled some robot at some node, and then you are coming back again via some backage, that robot is already crashed, or let's say even, or what happened, that robot is not there, then can immediately know that that robot is all, I mean, that node is visited, right? At least you know that, make sure that that is crashed or something happened. If it is a Byzantine robot or something, then it might move from there, then you can easily blacklist that Byzantine robot. So this kind of, I mean, information might help you to get something do faster. But for the other, I mean, that's why I'm saying it's actually depending on the context. It might be helpful in some of the context, in some of the cases, but maybe not, I mean, when you are just considering strict with memory and other things. But at least, I mean, if you remember few nodes, still that might help. So that's a plus point, but it's not yet fully analyzed. I mean, even we haven't actually thought on that way, like what will happen. I mean, whether even if you have IDs, whether you can do better or not, in just without any faulty and other things.
Also, I just want to add one thing to Anisir's point. So currently, this part of the tutorial is most of the vanilla setting. In a lot of the papers Anisir talked about, there was a strong focus on reducing memory, trading off memory with time. So in that case, yes, it's not been analyzed properly. Perhaps you could do something interesting there. A fair point. In a lot of the extensions where you have, let's say, fault tolerance and other things, there are some papers that still also trade off between time and memory. But a lot of those papers, it's more about dealing with that particular setting or that particular issue. And so in those cases, we don't mind if the robots have more memory. And the moment robots have a lot of memory and nodes have IDs, you could implement a simple preprocessing step. But that's a very valid point. When you don't have enough memory, what can be done?
Yes, one more question.
I guess I was wondering what this preprocessing step, if your starting configuration was almost perfectly dispersed, then in that case, everyone still gathers in one node and then disperses again. It seems quite a bit worse than what the optimal solution could be for that starting configuration.
Should I say it again? So it's about like if your starting configuration is almost dispersed already, does it really make sense to gather everything at one point and disperse it again?
For the grid one, or see, if you so once you have a gathering configuration, then of course it's easier to do that. But the algorithm, basically the arbitrary graphs or for arbitrary configuration, they are not doing that actually. Those who are already dispersed, they are dispersed. The undispersed basically robots, they are trying to find the other places. Okay. But for the grid one, actually what we are doing, I mean, we are just all considering for taking in a corner node in the gathering in a node, and then we are dispersing it, because then we have a clear view. Otherwise, I mean, I don't know. I mean, maybe you have the solution, but the solution we said, like, you are first gathering at a corner node and then we are dispersing it. But for the arbitrary graphs, I mean, for general graphs, I mean, if it is not grid, then it's, you don't need to do that actually.
Makes sense. Yes, now we can take a coffee break and
Yeah.
I guess you can decide when we reconvene.
Yeah.
Well, I mean, to keep in line with PODC, shall we reconvene in, I guess it's 3:15 now, right? Sorry, what is it? It's 10:15 over there, right?
Or maybe you can wait another 5 minutes more. I think that's fine.
Okay, I see. So let's reconvene at 10:35. Is that okay for everyone there?
Okay. I see you.
Okay.
All right. See you guys at 10:35.
Okay. Thank you. Thanks, Shreyas.